So we will start with our discussion for chapter 7, which is the alkenes and alkynes. So for this one, I'm using the 12th edition. That's why I'm saying some parts of the elimination reaction will be repeated for this. Na-share na ba na po? Okay, so chapter 7 is alkenes and alkynes 1. Same siya with the 11th edition and 12 for Solomon's, but for this case, I'll be using the 12th edition. And what's the difference between the 11th and the 12th? Well, in the 11th, they already talked more on the elimination reaction. So for chapter 7, saka pa lang sila, they're talking of the elimination reaction in the 12th edition. So the one that we discussed in chapter 6 might arise again as we go through chapter 7. So we've learned in general organic chemistry, first one, organic chemistry of our alkenes. Alkenes are also called olefin from the word olefiniant gas, oleum, which is oil, plus here to make because gaseous ethane. So the ethylene is the simplest alkene, the olefin, and the alkenes are considered or often called olefins. No? And they easily react with chlorine to form C2H42, a liquid oil. And so the most striking feature of an alkene when you look at the structure is it contains a double bond, CH2, double bond. And for alkyne, it you will see 3 bonds. No? For alkenes, it utilizes an sp2 hybrid orbitals. Of course, the geometry is planar. For alkynes like ethine, it utilizes an sp hybrid orbital and it's linear. The properties of alkenes, alkynes are similar to that of the alkanes. And alkanes up to 4 carbons except 2 butane are actually gases at room temperature. And of course, having contain only carbon and hydrogen atoms, we expect our alkenes also to be nonpolar themselves. And because of that, they only dissolve in nonpolar solvents or in solvents of low polarity. Okay, alkenes and alkynes are only very soluble in water, with alkynes being slightly more soluble than alkenes. No? So alkynes, why is that? Because alkynes are more ionic in character than the sp2 alkenes. The densities of alkenes and alkynes are lower than that of water, so they are less dense in water. Okay, so for naming our alkenes, there is a way of naming them, the easy system. We've learned before in chapter 4 of the cis-trans isomers, no? Cis-trans alkene. We can, I don't know if you can hear my background, no, but I really hate my background right now. So you have the cis-trans isomers. We've learned that in chapter 4. But when our alkenes are tri-substituted or tetra-substituted, no, the cis-trans are very ambiguous. It doesn't apply at all. That's why we'll be using from now on the easy systems for naming our alkane. So this one is based from the Kahn-Ingold Prelog convention no, in chapter 5.7. When we are determining the priorities of our groups of atoms attached to our double bond carbon. So again, the system uses the easy system applies to alkene diastereomers of all types. So how to use the easy system? Examine the two groups of atoms attached to the carbon atom of the double bond and decide which one has a higher Kahn-Ingold Prelog priority. Of course, it depends on the atomic number. You know? So for example, in carbon, this carbon between chlorine and fluorine, this chlorine would be of a higher priority, and for this atom, carbon, bromine would be of a higher priority than hydrogen. So you expect this higher priority to be the higher priority are on the same side, then we name that one as a Z alkene. If the higher priorities of each carbon atom are on the opposite side, so we name that one to be in the E. So the trans actually of a higher priority, the higher priority atoms on the double bond in a trans manner are actually are called E. This one for the same side, higher priority, the double bond is considered to be in the Z, named as Z stereoisomers, so Z and E. So of course, when you already learned fluorine and chlorine would have a higher priority than chlorine. So let's say, for example, in this 2-butene, 1, 2, 3, 4. So for this carbon atom, CH3 with a higher priority than hydrogen, and also for this second carbon, CH3 would have a higher priority, and the higher priority are on the same sides. We name this one as cis or Z, 2-butene or cis 2-butene. This one is easier because the other atom for each carbon is just hydrogen. So the Z and the cis are just the same. The E and the trans are also just the same. So where does it came from? Z came from the German word zusammen, which means together, and E comes from the German word entegen, which means opposite. So that's Z and E. Okay, just this one is already has an answer, like 1 bromo 1 to dichloroethanes. Of course, we want to know what is the configuration. Is it a Z or E? So you have to check for this. It's clear it's chlorine. For the second carbon, chlorine and bromine would have a higher priority. So chlorine and bromine are on the opposite side. So therefore, they are have a configuration that is E. 1 bromo 1 to dichloroethane. This one, they're on the same side. So this configuration of C. Okay, let's practice letter A. Anyone? Can you tell whether it's a Z or E? Can we designate whether it's an E or a Z? Can I have a volunteer? Anyone?
Hey, ma'am.
Okay, letter A is they are on the same side or opposite side. So this one, the priority is of course this H2, H2, H3, and for this carbon it's Br, so they are on the opposite side. So it is designated as E. Okay, so it's very simple. So now let's go to the relative stabilities of alkenes. So cis and trans isomers of alkenes do not have the same stability. Why is that? Strain can cause crowding of two alkyl groups on the same side of a double bond, which makes the cis isomers generally less stable than the trans. So the trans are much more stable than the cis. So this effect can be measured quantitatively by comparing the thermodynamic data from the experiments involving alkenes with related structures. So here you can see now these are the cis alkenes. They're the same side. So this one, the alkyl groups are situated very close to each other, and of course their electron density are very close to each other, and there could be greater repulsion between these two groups, right? So if you compare when the alkyl groups are on the opposite sides, okay, there is less repulsions, and you expect this trans to be more stable. There is less crowding, no, in this case. Other this one, there is more crowding, which promotes greater repulsion between these two groups. So again, for the trans, they are more stable than the cis isomers. Now let's look at the heat of reaction, no, to see which of the alkenes would have greater stability from the heat of the hydrogenation. So the alkenes can readily Okay, so again, the alkenes can readily react with hydrogen in the process called hydrogenation to form your alkane. And from here, we can have the heat of hydrogenation, no, produced in the reaction. So from this reaction, we can gain quantitative measures of the relative stabilities of alkene by comparing the heats of hydrogenation for family of alkenes that that would produce the same alkane as a product. Okay, let's consider. Okay, let's consider 3 isomeric alkenes. No, you have 1 butene and 2 butene and another 2 butene. This is a cis. This is a trans. When we do hydrogenation reaction, we react with hydrogen to form your 4 alkane. No? So when the reactor is this heat of hydrogenation is being formed, energy released in the form of heat. No? For cis 1 to 3, for cis for 1 butene, we produce negative 127 kilojoules per mole. And then you have the negative 120 for the cis, and for the trans, negative 115. Okay, you've noticed here that the one that has the lowest heat of hydrogenation is the trans alkene. And the as compared to the cis, and compare the 1 degree or the less substituted alkene here would have the highest degree of hydrogenation. So this data indicates that the trans isomer, the trans is more stable than the cis, this one. And the terminal alkene, like this one, is less stable than the disubstituted. Okay, so we can infer from this experiment that it's already stated here. The 1 alkene or 1 butene is less stable than the disubstituted alkene here. In fact, we can have a general trend of the relative stabilities of alkenes. No, the order of stabilities is that a tetra-substituted alkene is much more stable than the tri-substituted alkene than the di-substituted alkene. So the di-substituted alkene, the one located in the same carbon, is much more stable than the trans di-substituted alkenes and then the cis. And then the least stable alkene is the one with having only one alkyl group attached to it and then an unsubstituted alkene. So part of this explanation for this trend lies in the electron releasing effect of the alkyl groups. What I mean by electron releasing, it's an inductive effect, no, that try to donate an electron to its neighboring atom, and an effect that satisfies the electron withdrawing properties of the sp2 hybridized carbon atoms. So it will try to stabilize the sp2, the higher the alkyl groups, no. Again, as I've mentioned before, the alkyl group would have an electron donating inductive effect. Kaning giingon niya nga electron releasing effect is just similar to the term electron donating inductive effect. Parihara na siya. Maybe I should write here. Parihara na siya sa the R as an electron donating, electron donating or releasing. That could help to stabilize the carbonyl carbon, which is sp2 hybridized. So the sp2 hybridized atom would have an electron withdrawing effect. No, it's more vacant on its there's only 1/3 S character in there. So the order of stabilities, you have that. The greater the number of attached alkyl groups, the greater is the stability of the alkene. Okay, let's try to compare 2-methyl-1-pentene and 2-methyl-2-pentene. Anyone? Can we have a volunteer? Which one? Anyone? Almeda. Ayan. Ayan.
Yes, ma'am.
Between the two, which one would be the more stable alkene?
2-methyl. Hindi na may answer, ma'am.
Hindi na naman the answer. So of course, the tri-substitute, hindi naman the answer. It's easy to see. Pinanay. So of course, if you are just given no with a structure or with a name without a structure, you really need to write on the structure for you to see whether it's monosubstituted, di, or tri-substituted. Okay. Rank the following alkenes in order of increasing stability. Which one is the most stable? Erniel. Erniel,
Yes, ma'am.
can you tell me which one is the most stable alkene here?
B, ma'am.
The first, second, or the third?
Second.
One and second one. Okay, you can identify the first. Is it di, mono, di, tri, or tetra substituted alkene? The first one. Can you identify that one? Is the first one mono? Which, when you say mono, there's only one alkyl group that's attached to your alkene, right? Di, if there are two alkyl groups. Three, there are tetra, if there are three. I don't know. Okay, so can you identify for first one, is it mono, di, tri, or tetra substituted alkene? For the second one na lang. Sige, second one yung ang gikuan is
Oh, A na lang, ma'am. ADA, ma'am. Ang first one. The
nanong
first one,
amen.
ma'am.
Nanong amen.
Because it has 8 um,
Because it is mono, di, tri,
monodated.
mono substituted.
Yes.
Are you sure? Are you sure? Okay, let's go back to
Yes, ma'am.
this one. Let's go back here. For the relative stabilities of alkene, this is your double bond. Okay, you have 2 carbons in the double bond. So R is the alkyl groups or the group of atoms attached to your double bond. If there are 1, 2, 3, 4, it means it's tetra substituted, and this is the most stable kind of alkene, followed by tri when there are 3 R groups attached to your double bond carbons. Di, pag there are only 2 groups attached to your double bond carbon. So di, daghan na siya if the R groups attach only to the carbon, to the first carbon, to one of the carbons of the double bonds, it's a di substituted. And if the dialkyl groups, 2 alkyl groups are in the transition, it's much less stable than the di substituted